Hello humans, my name is Professor Leach and today we're going to continue our discussion of integrating odd powers of secant. Yesterday, we found out that the integral of secant x is the natural log of the absolute value of secant x plus tangent x. I just introduced that and gave a hint as to how we find that integral. We use one of our favorite techniques of math. There are three great techniques in math. That is add 0, multiply by 1, and change your variables. And multiply by 1 is the one that we want to use in this case. I did not tell you what form of 1 we should use. But given what the answer looks like, it's not hard to figure out how we should construct our 1 to make the integral go. So we could figure that out with a little bit of effort. Or you could just say, I will just remember that the integral of secant x is the natural log of the absolute value of secant x plus tangent x plus c. Then we moved on to secant cubed. And we don't have substitution for this. This whole exercise has been about ruling out substitution for secant cubed, odd powers of secants without tangents. And so we started using parts. We tried putting 3 factors of secant in the u column, then 2 factors of secant in the u column, and then 1 factor of secant in the u column. And that's the one that we settled on did not make things worse. The big deal with 1 factor of secant in the u column was that there were 2 factors of secant in the dv column. And so when we integrate secant squared, we get tangent x. And tangent x pairs nicely with products of powers of secant and tangent. When we had 1 factor of secant, we introduced natural log of absolute value of secant plus tangent. That kind of made things messy. And when we had no factors of secant in the dv column, we ended up with an x. So we had to integrate things like x times secant cubed. And that was not following Leach's second rule of integration by parts, that is, don't make things worse. So, any questions before we continue on with this problem? So at this point, we have to integrate secant times tangent squared. We did not get a substitution because we have an odd power of secant and an even power of tangents. The substitution ones are even powers of secant, where we can substitute w equals tangent, or odd powers of tangent, where we can substitute w equals secant. But we do have an important thing here. We have tangent squared, and tangent squared can be written as secant squared. I can never just remember this, is 1 minus 1 plus secant squared. What is tangent squared? Sine squared plus cosine squared is 1. So if I divide by cosine squared, I get that tangent squared plus 1 equals secant squared. So tangent squared is secant squared minus 1. All right. I have no defense. It's just early. All right, so we're going to replace the tangent squared with secant squared minus 1. And let's see what that gives us. So we still have the secant x tangent x from our original application of parts. And now we're going to replace the tangent squared. So I still have this secant out in front. That's the secant from our original application of parts. But now the tangent squared from the v and the half of this du is going to be written as secant squared minus 1. And it's still a dx. So our secondary integral, we can break into 2 integrals now. So this is going to be minus an integral of secant cubed I'm going to distribute. So secant cubed minus secant. Minus and minus is going to make plus the integral of secant x to x. So I'll just distribute the secant. And I'll get a minus secant cubed x to x plus an integral of secant x to x. And I still have this original secant x tangent x from the original application of parts. So now we've come across, so now we have an integral that we know. We know the integral of secant x is the natural log of secant x plus tangent x. And this minus secant cubed x to x is the one that we're looking for. So this is what happened to us yesterday when we were integrating cosine. This is the thing that we have to watch out for. When the integral that we're looking for shows up on the side that we're working on. So integral of secant cubed x dx is the integral that we're looking for. So we should gather like terms. So that is why we traded our tangent squared for a secant squared minus 1. Because now we have the integral we're looking for. That's the cool thing that happened. The integral we're looking for showed up on the side we're working on. This is like when you spend half an hour looking for your keys and you find out they were in your hand the whole time. So the integral that we're looking for showed up on the side that we're working on. So the strategy is to add it to both sides. And then the integral of secant x is an integral that we know. So I'm going to add the integral of secant cubed to both sides of my equation. This started off with a secant cubed up here, and here's a minus secant cubed on the other side. So I'm going to add a secant cubed x to dx to both sides. So I end up with two integrals of secant cubed x, two integrals of secant cubed x to x is a secant tangent. That's the same secant tangent from the original application of parts. And then we have this plus the secant x, and we know the integral of secant x. That's the integral, that's the natural log of the absolute value of secant x plus tangent x. And then we have done our integration, so we have plus some constants. Then all we have to do, just like with cosine squared, is divide by 2. So the integral of secant cubed x to x is 1/2 the secant x tangent x plus a 1/2 natural log of secant x, absolute value of secant x plus tangent x, plus a 1/2. Plus c.
Sorry, Professor.
So,
when the half come?
This particular process is going to this process is going to follow for all your odd powers of secant. You can break them up by parts. Your secondary integral will have an even power of tangent in it. Convert that even power of tangent to secant, and you'll have your secant to, so if we had secant to the fifth, that would end up with integrals of secant cubed and integrals of secant. So it just builds on the previous ones. Just follow the same plan. We have to remember our rules for parts. dv has to be something that we can integrate. So what we're going to do is separate out two secants to be the dv that we can integrate. And then we'll take the derivative of the rest. Put them together in the parts formula. Even powers of tangent appear. Replace those with secants. And repeat the process. Any questions?
How did we get the half values?
The 1/2 came from the dividing by 2.
Oh, sorry, I didn't see that. Thank you.
The 2 came from adding an integral of secant cubed to both sides of the equation. So I added this one to this one up here. The integral, and this is what happened in our cosine squared yesterday. The integral we're looking for showed up on the side that we're working on. So I just add it to both sides of the equation. I gather the like terms.
Thank you.
Any questions? Now, if we want to if we want to find these integrals quickly, then clearly we're going to use a machine. So the point is that the exercise is not so that we know what the integral of secant cubed is. If at any point in the future we need to know what the integral of secant cubed is, I can't actually imagine a scenario after Calc 2 where you need to figure out what this integral of secant cubed is. But to figure it out, you would just look it up. You'd just be like, oh, looking up and say, hey, Google, what's the integral of secant cubed? The whole point is doing the stuff in between. Because it's good exercise. And it helps us understand things like how substitution works, and more importantly, why substitution isn't going to work in this case. And it reinforces some common things that happen when we're integrating things, especially integrating by parts. Integrating by parts has a uv minus the integral of v times du. It produces another integral over here. Sometimes that integral is a nice easy integral that we already know. Sometimes that integral is a substitution. Sometimes that integral is an integration by parts. And sometimes we just need to break it up to one that we know and the one that we're looking for. Any questions? Comments?
I'm a little confused about one part.
About what part?
About the secant cube and the secant x part.
So these two, we integrate. The secondary integral from parts is v times du. That's a secant x tangent x times another tangent x, so secant x tangent squared. I replace the tangent squared with secant squared minus 1. And then I multiply secant by secant squared minus 1 to get secant cubed minus secant. So use the distributive property here. So the integral, we're integrating secant cubed minus secant, and then secant cubed plus secant because of the minus. And then I could just break that up into two integrals.
Okay, got it. Thank you.
So the process just builds on itself. So if I had, for example, let's push this up one more level. So if, for example, we had the integral of secant to the fifth, x dx. So this is odd powers of secants. We know that this is resistant to substitutions. So we'll try parts. One strategy for parts is to break up the secants. We have to remember that dv must be something that we can integrate. And I know I can integrate even powers of secants. So one strategy might be to keep two of the secants here in the integral column, and then put the rest in the derivative column. This is based on the strategy that dv has to be something that you can integrate. So then we take derivatives on the u column. So the derivative is 3 secant squared x times secant x tangent x dx. And in the dv column, the integral of secant squared is tangent x. This is not the only way we could have set this up. It's just the first thing that I thought of because dv is I can integrate even powers of secants without tangents. So this is the first thing that occurred to me to do. So let's set this up with parts. Integral of u dv is uv, so secant cubed x, times a tangent x, minus the integral. I'm going to factor out the 3, times the integral of v times du. That's going to be secant cubed tangent squared. So that's going to give me a secant cubed and then the two tangents will make a tangent squared. And now I can do the same thing that we did before. Tangent squared is going to be replaced with secant squared minus 1. So my integral over here is going to be minus 3 integrals of secant cubed times secant squared minus 1. So that's going to be a secant to the 5th minus secant cubed. Secant to the 5th is the one that we're looking for. Secant cubed is one that we know. So let's do that. So I still have secant cubed tangent from my original application of parts, minus, well, we have 3 from the du, times the integral of secant cubed times secant x squared minus 1. So I'm going to have a secant cubed times secant squared minus 1. dx. Now we'll do the same thing that we did last time. I'm going to distribute secant cubed. And so this will become secant to the 5th x and then over here I'll have plus 3 integrals of secant cubed x because the minus 3 distributes. And I still have this first term here, secant cubed times a tangent. And so this is the same thing that happened in the previous problem. The integral that we're looking for has showed up on the side that we're working on. The other integral is one that we already know because we've been doing these in order. So the integral that we're looking for, We're looking for a secant to the fifth, and that's the one that we're looking for. So the integral that we're looking for shows up on the side that we're working on, and the other integral is one that we already know. I just need 3 copies of it. We'll do the same thing that we did before. I'm going to combine like terms. I'm going to add 3 copies this time of secant to the fifth. And so on the left side of the equation, I'll have 4 integrals of secant to the fifth. Then I'll have a secant cubed tangent from our original application of parts. Secant cubed x tangent x. Plus 3 and then I'm going to go grab the integral of secant cubed from the previous page. The integral of secant cubed was a 1/2 secant tangent plus a 1/2 natural log of secant x plus tangent x plus c. So I'll have a 1/2 secant tangent plus a 1/2 natural log of absolute value of secant x. I knew I wasn't going to fit it all. Dang it. Tangent x plus c. Then all we have to do is divide by 4 to get the secant to the fifth. So secant to the fifth, or integral of secant to the fifth x to x is 1/4 secant cubed tangent plus, let's see, 3/2 divided by 4 will be 3/8 secant tangent plus 3/2 divided by 4 is 3/8 natural log absolute value of secant x plus tangent x plus c. So this is one of those cases in math where there's no trick to it. It's just a simple trick. And the reason that I like doing these problems, first of all, is that trigonometric substitution, if we really have to do a trigonometric substitution, these are the things it's going to lead to: even powers of cosine and odd powers of secant. So we need to know our even powers of cosine, where we just use a double angle identity, and our odd powers of secant, where we just perform this iterative process. Although we now know integral of secant to the first, third, and fifth. And if I start asking for like this secant to this integral of secant to the 7th x, we can see exactly what we should do. I'll separate out 2 secants that we can integrate into a tangent. And then I know that this is going to happen. The integral that we're looking for is going to show up on the side that we're working on. If I started with an integral of secant to the 7th, then I'm going to have some constant times secant to the 7th. That's going to be the one that shows up. And then there's going to be plus some integral of secant to the 5th, which is one that we already know. That's why we should go in order.
Professor, would you mind explaining the ln secant tangent part?
The integral of secant is natural log of absolute value of secant plus tangent. That's one that we know. This one came from, the 1/2 came from the integral of secant cubed, and all that came from the integral of secant. So this is one that we have in evidence now. So that's just a thing that we know now. Just like we know that the integral of natural log of x is x ln x minus x. We just know that. Just like we know that the sine of pi over 6 is a half. Just like we know 7 times 8 is 56. These are all just things that we carry around with us in our heads at all times because we're calculus students. Any questions? So what you should do is grab yourself a secant to the 7th x and do the same thing. What you'll realize is that this has stopped becoming a calculus problem, or sorry, this has stopped being a calculus problem and has just turned into an algebra problem. If I gave like a quiz or a test or a final exam where you're integrating secant to the 7th x, the mistakes that you're going to make are in the fractions. Your fractions would be off. But you can predict what's going to show up. If we have an integral of secant to the 7th x, there'll be a constant times the secant to the 5th tangent, a constant times the secant to the 3rd tangent, a constant times secant tangent, and then a constant times the natural log of secant plus tangent. So we should start seeing these kinds of patterns. The thing that we're working out by doing the process is just what the constants are. The difficulty here is the algebra, not the calculus, because the calculus pretty much stopped when we decided to use parts. Took a derivative, found an integral, then there was a trig question, then it was an algebra question, then it was just recognizing the thing that we're looking for and recognizing the thing that we already know. If you can't tell, I think this is fun. Because it's a nice little mystery. Because now we have a full suite of integrating products of powers of trig functions, powers of cosines and sines, powers of secants and tangents. We have set up some standard operating procedures for when we can use substitution, or for using substitution when we can. And we've covered the rest of our bases, because we can do even powers of cosine and odd powers of secant. So we can also see with this tangent squared being secant squared minus 1, why I didn't specify separately odd powers of secant and even powers of tangent. Odd powers of secant and even powers of tangent will just turn into odd powers of secant. Just like I summarized even cosines and even sines as just even powers of cosine, because the sines can become, if we have even powers of sines, we can turn those all into cosines. That should be our focus, because that's the integral, that's the way we want to integrate. We don't want cosine to the 4th x, we want cosine of 4x. Any questions? So I have said it, but we should write it. What we're going to look at is a process called trig substitution. Some of you might be thinking, we're good at substitution. We know how it works. To which I respond, really? Are you sure about that? Because I got more substitution coming your way. So trigonometric substitution is where we're going to employ that third great trick of mathematics. Don't like the problem? Change your variables. Change the conditions of the test. This is also known as a Kirk. What we're going to have is we're going to have an integral of, say, a function of x to x, and we're not going to like it. It's going to have things that we don't like, specifically square roots of quadratics. That's kind of the defining thing that we're going to see in our integral here. And what we're going to do is make a trigonometric substitution to trade our integral f of x for some integral in theta d theta. Now this integral is going to have the form of products of powers of trig functions, the thing that we've been studying. So that g of theta to theta is going to be an integral of products of powers of trig functions. Then we're going to integrate. Probably this product of powers of trig functions is going to be even power of cosine or an odd power of secant. So this is where we use our integration techniques. And then so we have an antiderivative. But this is an antiderivative in theta, and what we need to do is translate back to integrals in x. To get to our antiderivative in x. So the technique for integrating is to not integrate in x, but to change variables to theta, integrate your even powers of cosine and odd powers of secant to get the antiderivative, and then go back to your original variable. That is the trigonometric substitution way. We go around it. Like I said, the three great tricks of mathematics: add 0, multiply by 1, change your variables. AKA pull a Kirk, change the conditions of the test. One thing you may notice is that I've put the discussion that we're working on, integrating products of powers of trig functions, after section 7.3. 7.3 was tables of integrals. So the section on tables of integrals is, hey, go look this up, because a lot of people have done a lot of work to write down all these integrals already. So we should look them up in the table. And if we had a physical copy of the book, we could flip it to the back cover, inside the back cover, and see kind of a partial table of integrals. Because that's how things used to be done. We used to just carry a book of integrals around with us, and then we would look up, there's a bunch of chapters for each different form that we're looking for. And we look up the integral that we're looking for, or take the integral looking for, and see which integral in the book it matches. For those of you who are younger than me, a book is a collection of paper that's all been glued together that has information in it. What it's like is like a bunch of web pages, but you don't need a computer or an internet connection to look at them. So nowadays, you could probably guess, if we need to know an integral, we'll just say, hey, Wolfram alpha, what is the integral here? Does that make sense? The point is not we're looking for things. The point is not that we're looking for things that we don't know. The point is that we're learning a technique that helps us find things. Not because in the future we're going to need to find those things, but because right now we need to train in these kinds of exercises. To answer this important question in the chat, are there any students here? I don't think there are any students here that are older than me. And the probability that I get a student that is older than me in any of my classes decreases as I keep getting older. It used to happen kind of a lot. I started 20 years ago. And so it'd be perfectly reasonable for me to walk into a room and have a bunch of students that are older than me. But now, I used to be able to walk into the room and like sit down in the classroom and blend in as a student. Now, if I walked in and just sat down where the students were sitting, people would be like, "Oh, why is the professor sitting in this side of the room? Does that mean we go on the other side? What's going on?" So now I'm not fooling anybody. You know what I mean? 30 years ago, I also looked young for my age. But now it's all caught up to me. It's like all the aging half just showed up in my late 40s. It's like, oh man, I forgot. We were supposed to be aging this dude. And then so I woke up one day and my hair was all gray and like stuff started breaking and falling apart. It's like I went out of warranty. It's like the warranty ran out and all of a sudden it's like, oh, hey, remember all those genetics that were keeping you from aging? I'm like, oh yeah, warranty ran out. I'm like, oh no. And it's like, oh, something's gonna hurt now. Well, what's gonna hurt? Don't know.
You should have started your classes sitting in the back, so when class starts, everyone's like, "Where's professor?" and you just pop out of nowhere.
Yeah, no, it doesn't work anymore because if I sit in the back, people can just tell. It's like, oh, why is the professor sitting back there? Why is he acting all weird? Anyway, what are we talking about? So, I know this is a lot of technique. Once we get into trigonometric substitution, we want to notice that there are 3 distinct parts, and we've covered this part down here. The next thing we need to do is figure out how to go from our integrals that we don't want to our products of powers of trig functions that we know how to integrate. Then we also need to learn how to untrig sub. It's not as easy as with the regular substitution, where w is equals to x squared. So just replace all the w's with x squareds, and boom, you're done. Undoing a trig sub is a whole thing unto itself. But this will give us a really good picture of how substitution really works. And that is the point of the exercise. Because if we need to actually calculate integrals, we have machines for that. This one won't give us the actual integrals, but for the most part, we need values and not functions. And our calculator, even our ancient 90s calculators, can calculate the heck out of some numeric integrals. Any questions? Comments? Deep thoughts? So practice the integral of secant to the 7th x. If you think you got it, you should post it up in the discussion on integrating products of powers of trigonometric functions. If you have yet to post an integrating products of powers of trigonometric functions, that is a graded discussion. So make sure you jump on that discussion and make a post about one of the, there's like 10 to integrate because we've sorted out all the rules for how we're going to integrate things. So there's like 10 integrals that you can go in, pick a couple of them and integrate them, because that's the homework for tables of integrals. Next up, we're going to look at trigonometric substitutions, like I advertised. Apart from that, I believe that's it. I'm done. Email this to your grandma, and I'll see you some other time.